Hello and welcome to another video. In this video we're going to be working on unique binary search trees 2. So in this problem you're given an integer n and you want to return all the structurally unique BSTs which have n nodes of unique values 1 to n. Return the answer in any order. So for n equals 3 is our example here. We need to do this. So essentially what we need to do, the way this is going to work is you need to take every single node. So we have 1, 2, 3. We need to make a root. And then we need to take the left and the right and make all possible subtrees there. So for this, it's pretty straightforward. Like, let's say we're going to make a root here. So if 1 is the root, then we're going to say, okay, 1 is the root. Now, how do we split the left and the right, essentially, right? Like, what are we doing there? That's going to be our question. And so we need to actually try to build the left and the right at every single point, if that makes sense. So what we need to do is we need to say, okay, for a structurally unique BST, if 1 is the root, how many different ways can we do this, right? If 1 is the root, that means that this part has to be on the right side, right? So for this subtree, how many different ways can you do this for this 2, 3? So there's two ways you could do a 2, 3, right? You could either do 2, 3, or you could do 3, 2. And so essentially we're saying, okay, now let's recurse down. Once we say, okay, 1 is our root, we're going to say, let's take these two ways and let's actually combine those. And then for the left side of the tree, right? So for the left side of the tree is just null. So this part is just null always. But then for this right side, we need to say, okay, let's recurse down and let's actually get this part of it, right? So let's actually redraw all this and kind of explain it one more time in a better way. So if we have 1, 2, 3. Essentially what we're doing is we're trying every single root, and then we're saying, okay, for this root, let's recurse down, let's get all the left and the right combinations, and then let's add that to the root. So once again, we try this as the root. So if 1 is the root, we're going to have 1 here. Now we need to recurse. The left is nothing, so that's just a null node, and the right is this part. So when we recurse into 2, 3, we can either make 2 the root, in which case it would be like this, right? This is the only possible tree. Or we could make 3 the root, which would be 3, 2. And then this is going to return over here, and we need to plug in both of those to the tree with the root 1. So 1, 2, 3 would be like this, right? 1, 2, 3. Or we also have 1, 3, 2, both valid trees. And then this is going to be like this. All right, so we tried 1 as the root. Now let's try 2 as the root. So if we make 2 the root, let's actually get rid of some of this. And let's also get rid of this. So we're going to say, okay, let's actually change this color. We're going to make 2 the root. Now, what's going to be the left and what's going to be the right? Well, the left has to be this and the right has to be this. So for this, there's only one possible combination, right? It's always going to look like 2, 1, 3, because there's only one node on each side. So this is like this is the subtree with 2 as the root. So if we have 2, 1, 3. But you can kind of see what we're doing. We're just picking a node as the root, and then we're recursing one level down where we're saying, okay, for that, let's just make it a left and a right subtree and let's get all the combinations there. And then for all of those, let's just like loop those together. So for everything in the left and everything in the right, let's combine those in every way we can. It's going to give us all our nodes. Okay. And so now we tried that. Now let's make 3 the root, right? That's our last case. 3 is the root. So let's do this in another color. Yeah. So we're going to make this over here. Let's make this in blue. And let's also delete this. So we're going to say, let's make 3 the root. Now there's no right? So there's only left 1, 2. And so how many different ways can we make 1, 2? So 1, 2, you can do 2 different ways, right? You can either make 1 the root or 2 the root. So if 1's the root, you're going to have 1, 2. Or you can make 2 the root, and then that would be 2, 1. And so those are the combinations with 3 as the root. So actually, I didn't mean to delete this tree with 2 as the middle. So this was actually this tree here, 2, 1, 3. Okay, now for this, we have these two combinations that we're going to be returning. So for 3 as the root, we're going to have either 3, 1, 2, right? Or, and you can see the right is always null, or we're going to have 3, and we're going to have 2, 1. And these are our trees. And so this is all of our trees. And we can actually take a look. Did we miss any? So we do have 5 trees, and we do have 5 trees. So essentially, let's write down our algorithm one more time, just so we can kind of get a sense of what we're doing. Let's write it over here, and let's write it in different color. So we're going to have a left and a right value. And we're going to loop through Let's actually make this a little bigger after I type it so people can see it better. So let's loop through the numbers, and let's just set a root. Then we recurse the left and right side of the tree and get all valid trees for each. And then finally, we need to combine all those possibilities plus the root we picked into a tree, into trees, I guess, and store in the output. Okay, so essentially that's what we're going to be doing, and then we can make this, I think we can make this a little bigger, so it's like, there we go. That's what we're doing. We have a left and a right value, where it's just going to start with like 1 and n, and then we just pick a random root, like we're going to pick 1, we're going to pick 2, we're going to pick 3, and then we get the left and the right based on the root we picked. The left has to be less than the root, so if the values were like 1, 2, 3, 4, 5, right, and we picked 3 as the root, the left has to be this side, and then the right has to be this side, because all the values on the left have to be less than 3. So then we would be passing in 1, 5 initially, and then if we pick 3 as the root, the left would have 1 and 2, and then the right would have 4 and 5, and so on. And then obviously you can have the case where, like, let's say this is our root, then we're going to actually pass in 0 and 1, and that's going to symbolize, actually we're going to pass in 1, 0, and that's going to symbolize like an invalid index, so then we can just return none. Because you do want to return none for the empty node, because you are going to combine none with the rest of the tree. So like, if the right side of the tree is like this, let's say 2, 3, or 3, 2, the left side could just be the null node. And then we have to combine that with both of these. So the left is going to be null with this one, and the left is going to be null with this one. We have to try both. Okay? And there is also one more case. So there's actually the case where you're doing repeated work. So if you have like 1, 2, 3, 4, 5, and let's say we picked 4 as the root. Now this is going to be the left side. Now we pick 3 as the root. Now this is going to be the left side. Well, we could have also picked, you know, in this 1, 2, 3, 4, 5, we could have also just picked 3 as the root originally, and then this would be the left side. So you see, like, we're doing this 1, 2 multiple times, so we can also add caching here, where we can check if the left and the right is in our cache. Let's just give that back. You don't need caching for this one to work. It'll actually pass without caching and have a decent time complexity, but if you want to make it a little bit better, you can add caching. So let's code it up now. So we have a visited cache. Then we have a, let's just call it like builder or something. And we're going to have a left and a right here, so let's just call that left and a right. And we do have a base case where the left is bigger than the right. That means we don't have any valid nodes. So if left is greater than the right, let's just return the none in an array, right? You're returning an array of trees, so we're going to return a none tree, like a null node, essentially. Okay. Now, what we need to do is we need to be looping from the left to the right. So we need to say for I in range left right plus 1 because it's exclusive. Then here we're going to need to build our left and right. Oh, we also need to check our cache, by the way. So if left right in visited, return visited left right here, as always. So that's our caching. Perfect. Okay, now let's actually go through this loop where we're just setting roots. So whatever root we pick, we're going to have a left and a right. So we're going to say left equals, what are we going to do here? Or we can call this like maybe left children or something, or left subtrees, left trees, let's call it left trees, equals, this is going to be builder, and then it's actually going to be the left bound is the left, and then the right bound is going to be I minus 1, because if you think about it, like if we have 5 nodes, like 1, 2, 3, 4, 5, say, and I is 3, the right needs to be 2. And then if we pick this, then the right is going to be 0, so then we'll have 1, 0, meaning invalid tree, which means a null node, which is what we want, right? If we make the root over here, then the left side is to the left, and there's nothing there. Okay. So now we do right trees equals builder, and this is going to be I plus 1, right? So same kind of thing. If we pick the rightmost value, it'll also be out of bounds because we have 1, 2, 3, 4, 5. If we make 5 the root, then I plus 1 will be 6, so then we'll have 6, 5, which will also be left is greater than right, and we're going to turn the node, which is exactly what we want. Okay, so now we have our left and right trees. Now we need to take every single combination in both of them and add those together. So we actually do also need a result array, or we can just say we can do that here, I guess. So we can say like for tree, or we can say like left in a left trees, for right in right trees, right? Take every single combination, and every single combination needs to be added into a tree. And then what's the root going to be? Well, it's going to be I, right? We pick the I for be the root. So we can just say visited. Actually, yeah, let's actually make a result array here. So we're going to say result. We need to make that outside of the for loop, though. Let's make it here. Result is this. Then we could say res dot append, and then we're going to say tree node with the value of I, and then the left is going to be the left, and then the right is going to be the right. Right? This is the left subtree, this is the right subtree. So the left subtree is going to be left, right subtree is going to be this. We're going to append that to the result. Okay. And now we finally need to cache it. Equals the result, and we need to return it. Okay, so now we should be able to call return builder. And what are our initial values? So if you think about it, our initial values need to be 1 and n, right? They need to start from 1 to n. So our left is going to start at 1, our right is going to start at n. Okay, let's see what happens. Hopefully I did everything right there, maybe not. Okay, let's take a look. So this needs to be right. Okay. All right. And there we go. So you can see it's super efficient with the caching. So I would recommend you adding that. But if you didn't have it, it would also work. So it's just going to be a little bit less efficient. Okay. So I will also say for this, the time and space complexity is really confusing and really hard to derive. So I wouldn't expect to have to derive it in an interview. I would just say like kind of talk about what your function is doing roughly. You know, like you say, okay, for every single case, I am doing this for loop, and then I am cutting my array into a left, right, and a, so essentially, I mean, not exactly cutting the array in half, but on average, maybe cutting the array in half. So you could talk about it, but it's some crazy thing like 4 over whatever, like root n to the square, I don't know. Something that you can't come up with in an actual interview. But yeah, so that's going to be it for this problem. And if you liked it, then please like the video and please subscribe to the channel. And I'll see you in the next one. Thanks for watching.